Hello, everybody. So today we're going to be talking about how phase transitions vary with temperature. So before we really end up diving into that, we're first going to need to find a good way to describe when a phase transition occurs. And it turns out that one of our best bets for trying to describe uh, phase transitions is going to be by looking at free energy. So one of the big things that we can remember is that the two the two phases are going to be in equilibrium when the free energy of each component is equal. So if I have a liquid and a gas, if the free energy of these two species is identical, then it means it's going to be equally favorable to go from liquid to gas or gas to liquid, which will keep the whole system in equilibrium. And so in order to try and predict when a phase transition occurs, we can simply just look for the point at which these two free energies are equal. But here's where we have to kind of watch out, because free energy might not actually be the best metric when talking about the transition of two phases. Mostly because free energy is usually talking about the entire system. And in this case, we're just talking about one liquid component and one gas component. And this is going to become even more important when we start looking at mixtures. And so in order um, to emphasize that we're looking at the free energy of the individual components, we use what's called the chemical potential. So the chemical potential is essentially the molar free energy of a pure component. So let's say I have a mixture of water and salt. Well, I don't care about the salt, so I'm just going to be looking at the chemical potential or molar free energy of the water and the water vapor. So it's a good way so that you can try and ignore everything else that might be happening in the system and just looking at the one phase transition we care about. And so if a system's in equilibrium, we're just saying the chemical potential of, say, the liquid uh, is equal to the chemical potential of the gas or the liquid and solid, or whatever phase transfer we're looking for. So what this is going to help us do is try and figure out exactly when these two systems are going to be in equilibrium, because we already have a fairly good set of equations that will help us describe the Gibbs of a system. So if I'm going to be looking at how a phase transition is going to change with temperature, what I'm really going to want to look at is how the individual chemical potentials change with temperature. Because all I need to do in order to identify when the phase transition occurs is by simply determining when the chemical potentials equal. So chemical potentials will show a variance with temperature, which is going to be the same exact variance as Gibbs free energy, because it turns out they're the same. So if you remember from last chapter, the change of chemical potential with temperature under isobaric conditions is going to be negative of the molar entropy. And again, same thing will hold if you would be looking at Helmholtz and volume. But remember, since we're using Gibbs, we also have to look at isobaric conditions. And so what this ends up showing is that that as I heat the system, as temperature goes up, if I have since all third law entropies have to be a positive number, the chemical potential will always go down. So again, the more I heat the system, the more stable the system becomes. But here's the thing, not everyone is going to be equal. And so each phase is going to have a different molar entropy, and as such, it's going to have a different temperature dependence. And this actually is what really ends up controlling phase stability. So for example, solids have a huge benefit as they have relatively favorable enthalpies, as they have lots of good intermolecular forces, but they also tend to have fairly low entropies. So for example, if I'm looking at ice, specifically ice 1H, it has a molar entropy of about 41 joules per mole. So again, not too bad, but not too great. And so then when I end up running into liquid water, it has a much higher or more positive enthalpy, meaning normally we'd expect it to be much less stable because it doesn't make as many good bonds. But it has a lot more configurations it can adopt, which means at higher temperatures, this entropic contribution overwhelms its lower starting point. And this is demonstrated by the fact that while ice has a molar entropy of about 41 joules per mole Kelvin, liquid water has a molar entropy of almost 70 joules per mole Kelvin, so almost twice as high, which lets it quickly overtake. And then again, we have water vapor, which has almost no enthalpic contribution, and especially if we treat it as an ideal system, it would have an enthalpy of 0. But as you increase the temperature, this is where things get really nice because it has a huge entropy. And this entropy lets it quickly overtake both the solid and the liquid. So at temperatures above 100 degrees C, it dominates with its molar entropy of almost 190 joules per mole Kelvin. So this is almost 5 times as great a molar entropy as a solid, and well over twice as high as a liquid. So again, this is what really drives vapor stability, is that molar entropy. And so simply by, and this is what is always going to drive a vapor's higher stability at high temperatures than a liquid or a solid, is the molar entropy contribution. However, it is also worth noting that we can use our knowledge of our chemical potentials and our entropies and enthalpies to help try and determine exactly at what temperature phase transition will occur. So for example, what I can do is I know that if I'm looking at a temperature of fusion, so when we have fusion of a solid into a liquid, this is going to occur when the solid and liquid have identical chemical potentials. And then we can insert our expression in terms of the enthalpies and entropies of both the solid and the liquid and set the two equal to each other. And then through a little bit of clever rearrangement, I can put all of my entropies on the left and all of my enthalpies on the right. Now, what you might notice here is that both these terms on the left share temperature, so I can pull that out. And the entropy of the liquid minus the entropy of the solid is, well, products minus reactants. So that is going to be the molar entropy of reaction. And similarly on the right with the enthalpy of reaction. So final rearrangement gives us a general expression for determining the enthalpy or the temperature of fusion. And it's worth noting, you can actually do this for any phase transition, because again, all phase transitions tend to have a negative and a positive enthalpy as the product is less stable than the reactant, and also a positive entropy as there's more configurations that can be adopted by the product over the reactant. So as long as these two have the same sign, it gives us a positive temperature of transition. If you ever end up with a reaction where the signs do not agree, you will notice that this will give you a negative temperature, indicating that this can't happen. And this is essentially a way of saying that either you will always favor the reactant or the product, depending on the system that you're looking at. So this helps us figure out how temperature plays in with phase transitions. However, don't forget, temperature isn't the only control we have on chemical potential. Pressure also plays a role. So next time, we're going to dive into the influence of pressure on phase transitions. Till then, take care.